There is one thing in physics that always forces me to stop and think seriously, not because it is too complex, but because it is so easily taken for granted. In 1905, when Albert Einstein published the special theory of relativity, he pointed out that time is no longer an absolute quantity. Two observers moving relative to each other can disagree about how much time separates two events, and even disagree about which event happened first. This effect is not philosophical speculation. It has been confirmed many times in the 20th century, from atomic clock time dilation experiments on airplanes in the 1970s, to the fact that today's GPS satellites must apply relativistic time corrections every microsecond to function accurately. So far, everything seems fine, but the problem starts when you dig deeper, when you draw space-time diagrams, when you use the Lorentz transformations developed by Hendrik Lorentz at the end of the 19th century and placed at the center of the theory by Einstein. You realize that before and after are no longer universal concepts, and that is when a very uncomfortable question arises. If the order of time depends on the observer, then what happens to cause and effect? Can a cause become an effect in another reference frame? Before you think this is just wordplay or a philosophical paradox, let me be clear. I am a physicist. I believe in equations, in mathematical structure, and in logical consistency. If a theory, when properly understood, allows causality to be violated, then that theory has a serious problem. And that is why this question cannot be ignored. Because from the moment we accept that time is relative, we are forced to answer this central question. Why, in a universe where now is no longer absolute, does the order of cause and effect remain firmly preserved? To answer that question, we need to recall that in 1905, Albert Einstein published the special theory of relativity and showed that time and distance are no longer absolute quantities. A time interval measured by a moving observer can differ from one measured by a stationary observer, and the length in one reference frame can be shorter in another. These effects are not just on paper. In 1971, the Hafele-Keating experiment flew atomic clocks around the Earth on jet planes and recorded time differences exactly as predicted by relativity. Today's GPS satellites also have to apply continuous relativistic corrections. Otherwise, positioning errors would accumulate to kilometers in just one day. However, all of this revolves around one single crucial point. Every observer, regardless of their state of motion, measures the same speed of light in vacuum, approximately 299,792 kilometers per second. No reference frame is privileged. This requirement forces space and time to be tightly bound together into a unified structure called space-time. And it is that structure that determines what can change and what must absolutely not change in the universe. If you truly accept that both time and distance depend on the observer's state of motion, then an absolutely vital requirement immediately arises for physics. There must exist at least one invariant quantity. Without such a quantity, every physical description would become arbitrary. A universe where each observer has their own version of reality with no common anchor would lack any stable structure, and science, in the strict sense, could not exist. It was in that context that in 1908, Hermann Minkowski, Einstein's former teacher at the University of Zurich, introduced an entirely new perspective. Space and time should not be regarded as two separate entities, but as two aspects of a single unified structure called space-time. From this viewpoint, the concept of space-time interval emerges not as a mathematical trick, but as a logical necessity. The space-time interval is not time plus space in the ordinary sense, nor is it some quantity invented to make the equations look nicer. It is constructed so that changes in time and changes in space can precisely compensate for each other. When one observer measures a longer time interval between two events, another observer in relative motion will measure a shorter spatial distance between those same events. But when time is multiplied by the speed of light, about 299,792 kilometers per second, and combined with spatial distance in the manner dictated by relativity, the final result, the space-time interval, always has the same value for every inertial reference frame. The core point here is not the specific formula, but the property of this quantity, the space-time interval, is invariant. You can change velocity from a few percent of the speed of light to 99%. You can switch from one reference frame to another using Lorentz transformations. You can rotate the space and time axis in any way relativity allows, but the space-time interval between two events remains unchanged. Because of this invariance, it becomes the most fundamental quantity for describing the relationship between events in the universe. In Newton's classical physics, causality is usually understood simply as absolute temporal order. Cause happens before effect. But in relativity, temporal order can differ for observers in different motion, as Einstein pointed out right from 1905. Therefore, measured temporal order cannot be the ultimate foundation of causality. Instead, what determines whether one event can influence another is precisely the space-time interval between them. If the space-time interval between two events is of the type that permits it, meaning there exists a path in space-time along which a signal moving no faster than the speed of light can travel from one event to the other, then the causal relationship between them is undeniable. Conversely, if the space-time interval does not allow it, then there is no way for the two events to influence each other, no matter which reference frame you choose or how you arrange the time axis. In this sense, the space-time interval is not merely an abstract geometric quantity. It is the criterion that classifies causal relationships in the universe. It tells you which events can lie in the causal past of another event, which can lie in its causal future, and which are completely causally disconnected. This is exactly why, even though observers may disagree about which clock runs slower or which ruler is shorter, they are still forced to agree on the causal structure of the universe. They can argue about individual times and distances, but they cannot argue about whether two events can influence each other, because the answer to that question is fixed by the space-time interval. If causality is established as a hard criterion for every physical model, then the next question that must be answered precisely is, in a universe where both time and distance depend on the reference frame, what ensures that all observers still agree on the causal order? The answer does not lie in some additional philosophical assumption, but in a property built right into the foundations of special relativity in 1905 and clarified geometrically by Hermann Minkowski in 1908, the invariance of the space-time interval. The space-time interval is designed so that changes in time measurements and changes in space measurements do not occur arbitrarily. They are tightly constrained to each other by the Lorentz transformations. When one observer measures a longer time interval between two events, another observer moving relative to the first at velocity v will measure a correspondingly larger spatial distance between those same events, exactly enough to keep the value of the space-time interval unchanged. This is not a coincidence. It is a direct consequence of the requirement Einstein said in 1905, every inertial observer measures the same speed of light in vacuum, approximately 299,792 kilometers per second. This requirement forces the transformations between reference frames to have a very specific mathematical form, and that form ensures the space-time interval is invariant. You can change your velocity from near 0 to 0.9, 9c, comma. You can switch to a completely different reference frame. But when you calculate the space-time interval between the same pair of events, you always obtain the same value. What matters is that this agreement does not depend on whether the observers exchange information with each other, or whether they use the same type of atomic clock or measuring rod. It is encoded directly into the mathematical structure of space-time. Each observer may slice space-time into space and time in their own way, but every valid slicing leads to the same conclusion about the space-time interval. That is why the space-time interval serves as a common language that all reference frames are forced to use, even though they disagree about almost every other quantity. When viewed this way, the role of the space-time interval with respect to causality becomes clear. Causality is not protected by everyone's clocks running the same way, because experiments since 1971 with atomic clocks on airplanes have shown they do not run the same way. It is also not protected by everyone agreeing on spatial distances, because length contraction has been confirmed in high-energy particle experiments since the mid-20th century. Causality is protected by a deeper invariant quantity, from which all individual time and space measurements are merely different manifestations. If the space-time interval between two events allows a path along which a physical signal can travel at a speed not exceeding the speed of light, then every observer is forced to recognize that a causal connection exists between them. No reference frame can eliminate that connection, because doing so would require changing the value of the space-time interval, which the Lorentz transformations do not permit. Conversely, if the space-time interval between two events does not allow such a signal, then no observer, no matter how they are moving, can create a causal connection between them without violating the fundamental structure of space-time. Here, causality is no longer an additional assumption imposed from outside. It is a direct consequence of invariance. This very invariance eliminates the possibility of contradictions, such as an event being both the cause and the effect of itself in different reference frames. Observers may argue about measurement details, but they cannot argue about whether a physical influence can propagate from one event to the other. That has been decided from the beginning by the structure of space-time. Therefore, when we say that the space-time interval is the foundation protecting causality, this is not metaphorical or conventional. It is simply a geometric property of the universe. Just as in classical Euclidean geometry, you cannot draw a triangle whose interior angles sum to something other than 180 degrees while remaining in the plane. In the space-time of special relativity, you cannot create a causal relation that violates the basic order while still respecting the invariance of the space-time interval. Every physical model that wants to describe this world must accept that constraint. If a model requires the space-time interval to change with the reference frame or loses its invariance, then that model simultaneously loses the foundation that protects causality, and with it, the ability to be a consistent scientific theory. As early as 1908, Hermann Minkowski emphasized that relativity is not merely a set of equations, but a geometric theory of space-time. The Lorentz equations give precise results, but they do not always help us visualize what is really happening. Therefore, throughout the 20th century, in both teaching and research, physicists have used a simple yet extremely powerful geometric tool, the space-time diagram. To avoid unnecessary complication, we usually retain only one spatial dimension and one time dimension. This simplification does not lose the essence of the problem, because the causal structure that relativity cares about is fully revealed even in this two-dimensional picture. On the diagram, the vertical axis represents time, usually measured in seconds, while the horizontal axis represents one spatial dimension measured in meters. Each point on the diagram corresponds to a definite event, that is, a specific location in space at a specific moment in time. If you mark the position of a particle at different times, for example, every microsecond in a high-energy particle experiment, and connect those points, you obtain a continuous curve. This curve is called the world line of the particle. Even in the case of an object at rest in space, such as an atomic clock fixed in a laboratory from 2020 to 2021, its world line on the diagram is still a vertical straight line. This reflects an important reality, There is no absolute at-rest state in space-time. Every object is always moving in the time direction. When an object moves through space at constant velocity, its world line becomes an inclined straight line. The slope of this line carries quantitative information about the velocity. In practice, people often choose the scale so that the speed of light in vacuum, approximately 299,792 kilometers per second, corresponds to lines at 45 degrees. This choice is not arbitrary. It makes the causal boundary of special relativity intuitive. Every valid physical signal must be represented by lines within or on that 45-degree boundary. A line steeper than 45 degrees would correspond to a speed greater than that of light, which relativity from 1905 to the present does not allow. It is here that the connection between geometry and causality begins to become clear. On the space-time diagram, reading the relationship between events becomes very direct. If from one event you can draw a straight line with a slope less than or equal to 45 degrees to reach another event, that means there exists a physical path allowing a signal to travel from the first event to the second without exceeding the speed of light. Such events can have a causal relation. Conversely, if there is no way to connect two events with such a line, then no causal connection exists between them, regardless of the temporal order they appear to have in any particular reference frame. What is remarkable is that this reading does not depend on the reference frame. Every observer, whether moving at 0.5 c or 0.9 c, can draw their own diagram with time and space axes rotated according to the Lorentz transformation. But the fundamental causal relations remain the same. Which events can influence each other and which cannot are still represented by the same structure. This is where the invariance of the space-time interval reveals its intuitive role. It is not the way you draw the axes that determines causality, but the common geometry that every valid diagram must obey. Therefore, the space-time diagram is not merely a pedagogical illustration. It is a way of encoding all the causal information of space-time into a single drawing. When looking at this diagram, you do not need to know the details of the clocks or rulers each observer uses. You only need to look at the direction and shape of the world lines to determine what is causally possible and what is not. For this reason, from the beginning of the 20th century to the present, the space-time diagram has been the standard tool for discussing causality and relativity, allowing us to move from abstract debates about time and distance to a much clearer question in the geometric structure of space-time. Does a valid physical path exist connecting two events? In everyday life, we say an object is at rest if its position does not change over time. For example, an atomic clock fixed in a laboratory from 2020 to 2025. But that description is only correct in a specific reference frame, and only when considering space alone. On the space-time diagram that Hermann Minkowski introduced in 1908, even an object called at rest in space is still moving in a very clear direction, the time direction. If an object does not change its spatial coordinates, its representation on the space-time diagram is a vertical straight line, with each passing second corresponding to a step upward along the time axis. This does not mean the object is not moving. It only means that its entire motion occurs along the time dimension. In other words, every object in the universe is traveling through space-time, even though in many cases we do not notice it. From this perspective, the concept of the world line emerges naturally and inevitably. The world line of an object is the set of all events that object passes through, represented as a continuous curve in space-time. Each point on this curve corresponds to a definite state of the object at a definite time. For example, the position of a particle recorded every nanosecond in an accelerator experiment at CERN since the 1980s. When you follow the world line of an object, you are following its entire history of existence, not just in space, but in space-time. If the object moves through space at constant velocity, for example, 0.6 times the speed of light, its world line will be an inclined straight line. If the object accelerates, decelerates, or changes direction, the world line will curve. But in every case, the world line remains continuous, reflecting the uninterrupted progression of the object through space-time. The physical significance of the world line lies in the fact that it allows motion to be described without privileging space or time. Instead of saying an object is at one position at one time and another position at another time, we say the object has a world line with a specific shape. That shape contains all the necessary information about the motion. This is especially important in relativity, where observers moving at different relative velocities may disagree about what is space and what is time. Each observer can draw their own space-time diagram, with axes rotated according to the Lorentz transformation. But the world line of an object still represents the same sequence of physical events. It may appear more or less inclined, but the set of events the object passes through does not change. Therefore, the world line is more objective than quantities such as velocity or acceleration, which depend on the reference frame. A key point is that every world line of objects with mass must obey a very strict limit. Their slope on the space-time diagram can never exceed the slope corresponding to the speed of light in vacuum, approximately 299,792 kilometers per second, a value confirmed by electromagnetic experiments at the end of the 19th century and made foundational by Einstein in 1905. On the diagram, this means no physical world line can lie outside the region reachable by light. Even when changing reference frames and rotating the space and time axes as permitted, this boundary remains unchanged. From a geometric perspective, the speed of light is not just a measured number. It is a boundary in space-time, a boundary that every physical world line must respect. Once we accept that every object has a world line and that there is no absolute rest state in space-time, many familiar confusions begin to disappear. Motion is no longer a matter of an object moving through space over time, but of an object following a definite path in space-time. The differences observers measure in velocity, elapsed time, or path length can all be understood as different ways of slicing and measuring the same world line. In the context of causality, the concept of the world line plays a crucial role. A physical influence can only propagate along valid world lines, those that do not exceed the light speed limit. Therefore, whether one event can influence another depends directly on whether there exists a world line that allows connecting those two events. Once again, causality is not determined by subjective feelings of rest or motion, but by the shape and position of world lines within the geometric structure of spacetime. On the spacetime diagram proposed by Minkowski in 1908, a vertical world line represents an object whose spatial position does not change in the reference frame under consideration. For example, an atomic clock fixed in a laboratory for many years. Conversely, an inclined world line represents an object moving through space. The slope of this line increases with velocity as velocity approaches the speed of light in vacuum, approximately 299,792 kilometers per second. The world line approaches the 45-degree lines representing the motion of light. However, the difference between these world lines is not merely a geometric detail about slope. It is directly tied to a key physical quantity identified by Einstein in 1905, proper time. The length of a world line in space-time is precisely the measure of the proper time that object experiences along its history of existence. A clock attached to the object measures exactly this quantity, and each second that passes on the clock corresponds to a very small segment along the world line. When comparing two objects that start from the same initial event and end at the same final event, for example, two particles created simultaneously in an accelerator and detect it again after the same process, we find an important result. The world line of the object at rest in the reference frame under consideration has the greatest space-time length. The world line of the moving object, even though it may cover a greater spatial distance, has a shorter space-time length. This is the geometric manifestation of time dilation, which has been experimentally confirmed since the 1970s with atomic clocks flown on jet aircraft and later in high-energy particle experiments. As velocity increases from 0.5 c to 0.9 c or higher in modern accelerators, the world line becomes more inclined, and the accumulated proper time between the same two events decreases noticeably. This shows that velocity not only determines the shape of the world line, but also determines the amount of time the object actually experiences. A broader picture emerges when we do not just compare two individual world lines, but consider a family of world lines that start from the same initial event and are chosen such that they have the same proper time. The corresponding objects may move at very different velocities, from nearly at rest to nearly the speed of light, but if the clocks attached to them all register the same amount of proper time, for example exactly 1 microsecond since the initial event, then the ending points of those world lines are not distributed randomly on the diagram. Instead, they lie on a definite curve. This curve reflects the precise relationship between space and time in the space-time structure of special relativity. It is not like the familiar circles of Euclidean geometry, because in space-time, time and space are not symmetric like pure spatial axes. The shape of this curve is a direct consequence of the way the space-time interval is defined and of the requirement that this quantity must be invariant in every inertial reference frame. What is noteworthy is that this curve does not depend on who is observing or from where. Another observer, moving relative to the original one at, say, 0.8 c, can draw their own space and time axes differently via the Lorentz transformation. But when considering world lines with the same proper time, they still obtain the same form of curve. This shows that the relationship between velocity and world line length is not a product of a specific reference frame, but an objective property of space-time. The higher the velocity, the more inclined the world line, and for the same amount of proper time, the object will travel farther in the space of the reference frame under consideration, but advance less along its time axis. The entire relationship can be read directly from the space-time diagram without writing any algebraic equations. The curves that appear when comparing world lines with the same proper time are therefore not decorative geometric details. They are a clear sign that space-time has a structure very different from ordinary spatial intuition, and it is that structure that tightly regulates the way motion and time are bound together. Recognizing this is a necessary preparation for understanding more deeply how causal relations are organized in space-time. Because every velocity, every world line, and every amount of proper time is already constrained within the same single geometric framework, where physical limits are not rules imposed from outside, but direct consequences of the structure of space-time. From 1905, in the paper that laid the foundation for special relativity, Albert Einstein emphasized that the physical quantity of time with the deepest meaning is not the coordinate time assigned to an event by an external observer, but the time measured directly by a clock moving along with the object. That quantity later came to be called proper time. Geometrically, proper time is precisely the space-time length of the world line that the object follows between two events. Physically, it is the number of seconds that an ideal clock attached to the object would count as the object moves from one event to the other. The key point is that proper time does not depend on the reference frame. You can describe the same motion using many different coordinate systems, with space and time axes chosen differently through Lorentz transformations. But when you calculate the proper time along the object's world line. Every observer obtains the same value. This is not an assumption. It is a direct consequence of the invariance of the space-time interval, clarified by Hermann Minkowski in 1908. When an object is at rest in the reference frame under consideration, its world line is parallel to the time axis, and in that case, coordinate time coincides with proper time. But when the object moves, for example, at 0.8 times the speed of light, as in high-energy particle experiments since the 1960s, its world line becomes inclined. Then for the same amount of coordinate time elapsed in the reference frame under consideration, the space-time length of the corresponding segment of the world line is shorter, and therefore the proper time accumulated by the object is also less. This is the geometric content of the time dilation phenomenon. Rather than saying that motion causes clocks to run slow due to some physical mechanism, a more accurate way to express it is to say that different world lines between the same two events have different space-time lengths. An object moving faster through space will follow a more inclined world line, and between the same initial and final events, that world line has a shorter space-time length than a less inclined one. This phenomenon has been experimentally confirmed many times, from the Hathaway-Keating experiment in 1971 with atomic clocks flown around the Earth to measurements of the extended lifetimes of muons moving near the speed of light in accelerators at CERN. When two objects meet at the same initial event, then follow different world lines and meet again at a final event, the difference in the proper time each has experienced directly reflects the difference in the lengths of those world lines. No appeal to forces, acceleration, or any subsidiary dynamical effects is needed. The result is determined entirely by the geometry of space-time. Each clock on its own world line always functions normally and counts its own proper time consistently. No clock runs slow with respect to itself. The difference only appears when the clocks are compared after having followed different world lines. This perspective is especially important because it eliminates many common confusions when talking about time dilation. Proper time allows us to describe motion without privileging any reference frame. One observer may say object A is moving and object B is at rest, while another observer in relative motion may say the opposite. But both agree on the proper time each object has accumulated along its own world line. This shows that proper time is tied to the physical history of the object, not to the description of any particular observer. Moreover, proper time always increases along a valid world line, that is, a world line that does not exceed the speed of light limit of approximately 299,792 kilometers per second. This establishes a natural order for events occurring on the same world line. Although observers may disagree about the coordinate time order of events, they cannot disagree about their order according to proper time along that world line. This is a crucial point when discussing causality. A physical influence can only propagate along such world lines, and since proper time always increases in the direction of propagation, it is impossible for an event to be both the cause and the effect of itself on the same world line. Viewed this way, time dilation is no longer a strange or paradoxical phenomenon. It is a direct consequence of working in a space-time geometry where the lengths of world lines depend on their shapes, and where motion through space alters the way an object progresses through time. In special relativity, constructed by Albert Einstein in 1905, every inertial observer has the right to consider themselves at rest, and from that right, they construct their own time axis as precisely their own world line. This time axis represents the sequence of events the observer experiences with each second passing on their clock corresponding to a step forward along that axis. The observer's space axis, in the geometric representation proposed by Hermann Minkowski in 1908, is defined as the set of events that the person considers simultaneous at a given moment on their time axis. When a second observer moves relative to the first, for example, at 0.6 or 0.8 times the speed of light, the second observer's time axis no longer coincides with the original one. It becomes inclined on the space-time diagram, directly reflecting the relative velocity between the two frames. What is important is that the second observer's space axis cannot remain the same either. It must tilt by the same angle, such that the two new axes, the time axis and the space axis, are always symmetric around the lines representing the motion of light. This symmetry is not an arbitrary choice. It is enforced by the foundational requirement of relativity. Every inertial observer must measure the same speed of light in vacuum, approximately 792 kilometers per second, a result confirmed by electromagnetic experiments at the end of the 19th century and placed at the center of the theory by Einstein in 1905. If you try to tilt the time axis without correspondingly tilting the space axis, the light lines would no longer sit at 45 degrees on the diagram, and the speed of light would then differ between reference frames, which is not allowed. Therefore, in space-time, changing reference frames is not like a rotation in familiar Euclidean geometry. In ordinary geometry, you can rotate spatial axes while preserving lengths and angles between lines. But in space-time, this rotation follows an entirely different rule. The new axis must be chosen so that the light lines remain at 45 degrees. This rule leads to a very special transformation, where time and distance intervals in the new frame are formed from a precise combination of time and space in the old frame. That transformation is the Lorentz transformation, formulated as equations by Hendrik Lorentz at the end of the 19th century and given full physical meaning by Einstein in 1905. However, rather than starting from the formulas, we can understand this transformation entirely through geometry. You begin with a space-time diagram of the first observer with the time axis vertical and the space axis horizontal. Then you draw the time axis of the second observer as an inclined straight line corresponding to that person's relative velocity. The second observer's space axis is drawn as the set of events they consider simultaneous, and this forces that axis to tilt in a definite way, symmetric to the time axis around the light lines. When the two new axes are erected, you can draw lines parallel to them to form a new coordinate grid. This grid represents the way the second observer assigns space and time coordinates to events. What is remarkable is that the intersections of the old grid and the new grid do not disappear or change. They still represent the same physical events that occurred at definite positions and times in space-time. Only the way of labeling coordinates for those events changes. This is the core geometric meaning of the Lorentz transformation. It does not move events in space-time, but only changes the coordinate axis used to describe them. When observing world lines and the curves representing equal proper time on the diagram, we see that they retain their essential nature when changing reference frames. A straight world line in one frame remains a straight world line in the other. Though the inclination may differ, the curves representing points at the same space-time distance from an origin remain the same type of curves, even though they are cut by the coordinate grid in different ways. This directly reflects the invariance of the space-time interval. The Lorentz transformation is designed precisely to preserve this quantity. Every valid transformation between inertial reference frames must keep the space-time interval between events unchanged, and therefore preserve the causal structure. When viewed through this geometric lens, many consequences of relativity become clear. The fact that observers disagree about simultaneity is no longer mysterious, but a direct consequence of their space axes being tilted differently in the same space-time. Time dilation and length contraction are no longer isolated effects, but consequences of measuring segments of world lines and spatial intervals in different directions within the same geometric structure. Most importantly, the Lorentz transformation appears not as an arbitrary mathematical trick, but as the only way for different observers to describe the same space-time, while still agreeing on the speed of light and on causal order. It is clear that the space and time coordinates of an event can change dramatically when shifting from one reference frame to another. An event may occur at t equals sine 10 microseconds in one frame, but be assigned t equals sine 25 microseconds in another frame, moving relative to it. The spatial distance between two events may be a few meters in one frame and tens of meters in the other. Such differences were well understood from 1905, when Albert Einstein constructed special relativity. But if every quantity changes in that way, what keeps the physical description from falling into contradiction? The answer lies in a single quantity that is not allowed to change the space-time interval. When Hendrik Lorentz constructed the transformations named after him at the end of the 19th century, and when Einstein gave them full physical meaning, the decisive condition of those transformations was that they must preserve the speed of light in vacuum, approximately 299,792 kilometers per second. This very condition forces the space-time interval between any two events to remain unchanged under every inertial frame change. If the space-time interval changed, the speed of light would no longer be invariant, and the entire structure of relativity would collapse. This invariance is not just on paper. On the space-time diagram, you can see it intuitively. When new axes are erected for a moving observer, the new coordinate grid may be tilted and stretched compared to the original, but the curves representing points at the same space-time distance from an origin retain their shape. They may be cut by the new grid differently, but the curves themselves are not distorted. This shows that the space-time interval is not a quantity tied to a particular coordinate system, but a geometric property of space-time itself. Every observer, whether moving at 0.3 c or 0.9 c, is looking at the same geometric structure from different angles. When accepting this, the connection between the space-time interval and causality becomes direct. Causality does not depend on who measures time faster or slower, nor on who measures distances longer or shorter. It depends on whether there exists a valid physical path between two events that allows influence to propagate at a speed not exceeding the speed of light. The existence of that path is determined entirely by the space-time interval between the two events. If the space-time interval is time-like, meaning it allows a world line connecting the two events without violating the light limit, then every observer is forced to agree that one event lies in the causal past of the other. No frame change can reverse that, because doing so would require changing the space-time interval itself, which the Lorentz transformation does not permit. Conversely, if the space-time interval between two events is space-like, meaning no path exists that allows physical influence to travel from one to the other, then no observer can turn them into cause and effect of each other without breaking the fundamental structure of space-time. The invariance of the space-time interval thus acts as an absolute filter for causal relationships. It classifies pairs of events into those that can be causally connected and those that cannot, And this classification is completely independent of the reference frame. When observers disagree about the time order of two events, that can only happen in cases where the two events were already causally disconnected from the start. No frame change can turn a causally disconnected pair into a causally connected one, or vice versa. This eliminates the possibility of paradoxes, such as an event being both cause and effect of itself, simply by changing perspective. Each time you change reference frames, you only change the way coordinates are assigned to events, not the underlying physical relationships between them. Here the distinction between coordinate time and proper time, between measured spatial distance and space-time interval, becomes decisive. Coordinate time can differ between frames, but proper time along a world line does not. Spatial distance can change, but space-time interval does not. And because causality is tied tightly to these invariant quantities, it too cannot be altered by changing reference frames. Viewed this way, the Lorentz transformation is not the source of paradox, but the mechanism that protects us from paradox. It ensures that although observers may disagree about how to slice space-time into space and time, they still agree on what matters most, the causal structure of the universe. This is not a side consequence, but the deep reason why relativity was built the way it is. In the familiar spatial geometry from Euclid, more than 2,000 years ago, if you keep the distance to a fixed point constant, the set of points satisfying that condition forms a circle. But when moving to the space-time of special relativity, established by Albert Einstein in 1905, and given geometric interpretation by Hermann Minkowski in 1908, this intuition no longer holds. Here the quantity held fixed is not spatial distance but space-time interval. When you keep the space-time interval to an origin event constant, the set of events satisfying that condition does not form a circle, but characteristic curves called hyperbolas. These curves arise directly from the mathematical definition of the space-time interval, and from the requirement that this quantity must be preserved under Lorentz transformations, constructed by Hendrik Lorentz at the end of the 19th century, and placed at the center of physics by Einstein in 1905 on the space-time diagram. Hyperbolas act as lines of equal interval. Every point on the same hyperbola has the same space-time distance to the origin event. What is important is that this hyperbolic shape does not depend on the reference frame. You can switch to another frame, moving at 0.5 c or 0.9 c, comma. You can rotate the space and time axes according to the Lorentz transformation, but the hyperbolas retain their shape and relative positions in space-time. This shows they are not tied to any specific coordinate assignment, but to the objective geometric structure of space-time. The physical meaning of the hyperbolas becomes clear when we connect them to world lines. Consider a family of objects starting from the same initial event. For example, at t equals sine 0 and x equals sine 0, and then moving inertially at different velocities, from near zero up to near the speed of light of 299,792 kilometers per second. If we select the objects so that each experiences the same amount of proper time since the initial event, for example, exactly 1 microsecond as measured by a clock attached to each, then the endpoint events of those world lines will not be scattered randomly on the diagram. Instead, they all lie on a definite hyperbola. This directly reflects the fact that proper time is the space-time length of the world line. The same proper time means the same space-time interval from the starting point, and the hyperbola is the geometry of that set. Thus, hyperbolas can be understood as level sets of proper time. Each curve represents all the events that an inertially moving object can reach after accumulating the same amount of proper time from an origin event. This perspective gives the hyperbolas a clear physical meaning, rather than viewing them as purely abstract mathematical curves. When changing reference frames, the coordinate axes change, world lines may appear more or less inclined, but the hyperbolas do not change. That shows they encode a deeper property of spacetime, independent of the observer's viewpoint. This meaning becomes especially important when considering causality. The spacetime interval determines whether a physical influence can propagate from an origin event to another event, and hyperbolas provide an intuitive way to compare degrees of causal distance. Two events on the same hyperbola have the same spacetime interval to the origin, meaning that in terms of the possibility of transmitting influence at speeds not exceeding the speed of light, they are equivalent causally. A signal starting from the origin event, if following a valid world line, would require the same amount of proper time to reach any event on that same hyperbola. Therefore, hyperbolas can be seen as lines of equal causal depth in spacetime. They do not indicate the coordinate time order of events, because that order depends on the reference frame. Instead, they indicate which events are at the same level of causal possibility relative to an origin point. Viewed this way, we see that causality is not organized according to flat time slices, as in 19th century classical intuition, but according to curved structures in spacetime. A validly moving object or signal progresses from closer hyperbolas to farther ones, reflecting the continuous increase of proper time. It cannot reverse back across those hyperbolas without violating the fundamental structure of spacetime. From the fact that hyperbolas represent sets of events with the same spacetime interval, we can extend the perspective and describe the entire structure as a causal landscape of spacetime. This term is not intended to create an emotional image or literary metaphor, but to emphasize the precise geometric function of spacetime in organizing and limiting causal relationships. This idea emerged clearly from the early 20th century, when Albert Einstein and later Hermann Minkowski pointed out that the spacetime interval, rather than coordinate time, is the foundational invariant quantity. As an invariant quantity, the spacetime interval allows classification of events not according to the time order measured by clocks in a specific reference frame, but according to the degree to which they can physically influence each other. The hyperbolas act as level sets in this structure. Each curve defines a set of events with the same spacetime interval relative to an origin event, such as an event occurring at t equals sign 0 and x equals sign 0. The entire spacetime can be viewed as stratified by these level sets, and what is important is that these layers do not depend on the reference frame of any observer, whether moving at 0.2c or 0.9c. An object or physical signal described by a valid world line that does not exceed the speed of light of 299,792 kilometers per second will continuously move through these layers in a definite order. That order is determined by the increase of proper time along the world line and cannot be reversed while still respecting the structure of special relativity. This allows causality to be described as a global structure of spacetime, rather than as a local convention tied to individual proper time measurements or to a specific coordinate system. In this structure, each event occupies a definite position, and the causal relationship between events is determined by whether a valid world line exists connecting them. The causal landscape divides spacetime into different regions relative to each origin event. Events lying in the region where the spacetime interval permits a world line with speed not exceeding that of light to reach them belong to the causal future of that event. Conversely, events lying outside this region, even though they may be assigned different after or before times in different reference frames, still cannot be causally influenced by the origin event. This division is absolute because it is based on invariant quantities and does not change when switching reference frames. Different observers may choose different time and space axes, may slice spacetime into different coordinate time slices, but they are all describing the same causal landscape. This is precisely what explains why disagreement about simultaneity, widely discussed since 1905, does not lead to disagreement about causality. The causal landscape also defines a preferred direction along each world line. Proper time always increases in one unique direction on valid world lines, and this corresponds to moving from layers with smaller space-time intervals to layers with larger space-time intervals. This direction is not the result of a convention or of how humans measure time, but a direct consequence of space-time geometry. Therefore, although reference frames may reverse the coordinate time order of causally disconnected events, they cannot reverse the order along a world line. There exists no valid path that allows an object or signal to return to previously traversed space-time interval layers without violating the basic geometric structure of space-time. An important consequence of this perspective is that causal limits do not need to be imposed as external prohibitions on the theory. They are not supplementary rules designed to prevent paradoxes, but intrinsic properties of space-time geometry. If a physical process proposed in a theoretical model can be fully described by world lines lying within this permitted landscape, then causality is automatically preserved. Conversely, if a model requires world lines to go outside that structure, for example, demanding signals faster than light or reversing back across space-time interval layers, then that model directly conflicts with the geometry of space-time and therefore cannot be accepted within the framework of relativity. The causal landscape thus serves as a geometric test standard for every physical description, allowing an objective evaluation of whether a proposed process can occur in the universe. Within the framework of relativity, the question of the flow of time is not answered by subjective feeling or psychological experience, but by very specific geometric properties of space-time, laid down in 1905 in Albert Einstein's work and systematized geometrically in 1908 by Hermann Minkowski. Along every valid world line, that is, world lines describing motion at speeds not exceeding the speed of light in vacuum, approximately 299,792 kilometers per second, proper time always increases in one unique direction. This is not an additional assumption or philosophical convention, but a direct consequence of the way the space-time interval is defined in special relativity. Each infinitesimal segment of a time-like world line has a positive space-time interval, and when integrated along that world line, the total proper time measured by a clock attached to the physical system always increases as the system advances from one event to the next. No Lorentz transformation exists that can reverse this order, because every observer, whether moving relative at 0.1 c or 0.9 c, agrees on the value and the direction of increase of proper time along the same world line. This is what allows a precise definition of the concept of future in relativity. The causal future of an event is the set of events lying on world lines where proper time increases from that event onward. The flow of time in this sense is not a flow of space-time itself as an independent entity, but the way physical systems are forced to move within the geometric structure of space-time. An object does not choose the direction of its proper time. That direction is fixed by the geometry, just as an object in flat space cannot arbitrarily change the sum of angles in a Euclidean triangle. On the space-time diagram, this corresponds to valid world lines, always crossing equal interval hyperbolas in a definite order, going from smaller space-time interval values to larger ones. A physical system may accelerate, decelerate, or change direction in space, thereby altering the inclination of its world line, but it cannot reverse the direction in which proper time accumulates. Even when different observers, as emphasized in analyses from the early 20th century, slice space-time into different coordinate time slices and assign different time orders to events, they still cannot reverse the increasing order of proper time along a world line. This explains why reference frames can disagree about the time order of causally disconnected events, but cannot disagree about the direction of advance of time for a specific physical system. The flow of time, understood in this way, is not tied to a global time axis common to everyone, but to each individual world line, each carrying its own clock. More importantly, the structure of space-time does not permit the existence of valid world lines on which proper time decreases. Such a scenario would require segments of world lines with negative space-time intervals in the reverse direction, which can only occur if speeds exceeding that of light are allowed, or if the invariance of the space-time interval is broken, both excluded in special relativity. Therefore, every description of time travel backward lies outside the geometric framework established in 1905. The flow of time, in this context, is locked in by the geometry of space-time, rather than by specific dynamical rules or thermodynamic processes, such as increasing entropy, which was studied more deeply later, especially from the second half of the 20th century. Even before considering entropy or the thermodynamic arrow, the space-time structure already imposes a basic order on every physical process. Proper time always increases, and that increase is sufficient to define a preferred direction for causality. Dynamical equations may be time-symmetric in many cases, but their physical solutions still lie on world lines, where proper time increases progressively. The order of the flow of time becomes precisely defined when we introduce the concept of the light cone, a foundational geometric structure of space-time in special relativity. This concept arises directly from Albert Einstein's 1905 work, when the requirement was set that the speed of light in vacuum must have the same value, approximately 299,792 kilometers per second, for every inertial observer. For each definite event in space-time, the light cone is defined as the set of all world lines that a light signal can follow from that event. On a space-time diagram with one spatial dimension, this structure appears very clearly. Two straight lines inclined at 45 degrees emanating from the origin event, one pointing toward the future and one toward the past. These lines are not conventional choices or arbitrary illustrations. They are fixed by the finite and invariant value of the speed of light itself. The region between the two 45-degree lines toward the future is called the future light cone, while the region between them toward the past is the past light cone. Every valid world line of massive objects must lie entirely inside the light cone, because if a world line extends beyond this boundary, it is equivalent to the object or signal moving faster than light, an exclusion that has been both theoretically and experimentally ruled out for over a century, from early 20th century optical experiments to precise measurements in modern particle accelerators. The role of the light cone in limiting causal influence is direct and absolute. An event can only influence events lying within its future light cone, because only in that region do valid world lines exist that allow a physical signal to propagate without exceeding the light limit. Conversely, every event lying outside the future light cone is completely causally disconnected from the origin event, even though in a particular reference frame they may be assigned different after or before times. Similarly, the past light cone of an event defines the set of all events that could have influenced it, and this set is the same for every observer. This division is invariant. You can change reference frames, tilt the space and time axes according to a Lorentz transformation, but you cannot change the shape or position of the light cone attached to an event. This shows that the light cone is not a product of coordinate assignment, but an objective geometric property of space-time. When placing the light cone in the context of the causal landscape, built from space-time intervals and hyperbolas, we see that the light cone is precisely the geometric boundary, delineating the regions that can and cannot be causally connected. Hyperbolas stratify space-time according to space-time interval, while the light cone defines the absolute boundary between those layers, according to the possibility of transmitting influence. Inside the light cone, valid world lines exist, and proper time along them always increases, allowing a consistent causal order to be established. Outside the light cone, no valid world line connects the events, and therefore no causal relation exists, regardless of how coordinate time order may change when switching reference frames. The light cone thus functions as a geometric filter for every physical process. Whenever we ask whether a signal, a particle, or an influence can propagate from one event to another, the ultimate answer always reduces to whether a world line exists entirely within the light cone. If yes, the process is compatible with space-time structure. If no, it requires exceeding the light limit, and therefore breaks the causal structure. More importantly, the light cone is not merely local at each individual event. Since every event in space-time has its own light cone, these cones overlap and connect, forming a global network within which every valid world line must lie. The flow of time described earlier is precisely the flow of world lines, penetrating deeper into the successive future light cones of the events they pass through. A physical system advances into the future simply because its world line continues to lie within those future light cones, and no geometric mechanism exists that would allow the world line to veer outside and then return without violating space-time structure. At the same time, no reference frame change can turn an event outside the light cone into one inside the light cone. You can change your viewpoint, but you cannot change the boundary that the light cone defines. This is what ensures that causality is not threatened by the relativity of time and space. If the light cone defines the valid paths for every physical influence, then any assumption that permits a signal or object to extend beyond the light cone immediately places the causal structure in jeopardy. In special relativity, constructed by Albert Einstein in 1905, exceeding the speed of light in vacuum, approximately 299,792 kilometers per second, corresponds on the space-time diagram to drawing a world line outside the light cone. That is, a line steeper than the 45-degree lines, representing the motion of light. Such a line is not merely faster than light in a dynamical sense, but carries a very serious geometric consequence. It allows connecting two events that were previously space-like, separated, according to the Minkowski space-time structure presented by Hermann Minkowski in 1908, with a world line now considered valid under the new assumption. That means pairs of events that were formerly completely causally disconnected can now influence each other. But the problem does not stop there. When we combine the possibility of superluminal speed with the established fact from the early 20th century that different reference frames slice space-time into different time slices via the Lorentz transformation, an unavoidable consequence emerges. A superluminal world line, when described in one particular reference frame, may appear to go from past to future according to coordinate time. However, when switching to another reference frame, moving relatively with space and time axes tilted according to the Lorentz transformation, that same world line may have its time direction reversed in coordinate time. In other words, the same superluminal signal can be observed as traveling from future to past in a different reference frame. This is not a subtle effect that appears only in special cases. It is a direct consequence of space-time geometry, combined with the assumption of allowing superluminal speeds. When this occurs, causality is not merely threatened on paper, but specifically reversed. An event can serve as both cause and effect of another event, depending on the chosen reference frame. From here, causal loop scenarios, in which an event contributes to causing its own existence in the past, become unavoidable if world lines are allowed to extend beyond the light cone. These loops have been seriously analyzed in theoretical physics since the mid-20th century, not as logical games, but as indicators that a theory has lost consistency. When a theory permits such causal loops, it no longer provides a usable description of the physical world. Foundational concepts such as initial conditions, final conditions, prediction, and verification, which have been the core of experimental science since the 17th century, lose their meaning. What is important to emphasize is that the paradox here does not arise from the complexity of mathematics or from our insufficient understanding of the equations. It arises directly from breaking the geometric boundary of the light cone. Merely allowing one world line to extend beyond the light cone is sufficient to cause the entire causal structure to collapse. No need for imaginary devices or science fiction scenarios. The geometry of space-time itself ensures that superluminal speed equates to inverting cause and effect. This shows that the speed of light is not a random number inserted into the theory for historical or purely experimental reasons. It is the minimal boundary necessary to protect the causal structure. If the speed of light did not serve as the maximum speed, there would be no way to prevent the emergence of reference frames in which cause-effect order is reversed. Special relativity does not say that superluminal speed is merely not yet observed or not yet technologically achievable, like many other technical limits in the history of physics. It says that superluminal speed is incompatible with the very space-time structure that the theory describes. A model allowing superluminal speed does not merely add a new possibility. It fundamentally alters the entire foundational geometry of space-time. To avoid paradox, such a model would have to abandon the invariance of the space-time interval or abandon the relativity principle. And in doing so, it would no longer be relativity. Therefore, when we say that relativity does not allow superluminal speed, we are not invoking an arbitrary prohibition. We are saying that within the geometric framework of space-time established in 1905, superluminal speed and causality cannot coexist. Either you keep the light cone as the invariant boundary for every world line, or you accept irresolvable causal paradoxes. Relativity chooses the first option, and it is precisely that choice that keeps our universe describable in a consistent way. This model was systematically presented by Hermann Minkowski in 1908, 3 years after Albert Einstein published the special theory of relativity in 1905. Minkowski's spacetime describes an ideal universe without gravity, without curvature, where the laws of physics take the same form at every point and in every inertial reference frame. In this model, the geometry of spacetime is flat, in the sense that the geometric relations between events do not depend on absolute position or time. However, this flatness is not the familiar Euclidean geometry from ancient Greece. Instead, time and space are combined into a geometric structure with a different signature, inevitably leading to the appearance of objects such as the invariant spacetime interval, light cones, and hyperbolas. In Minkowski spacetime, every event has a clearly defined light cone, with boundaries fixed by the speed of light in vacuum, approximately 299,792 kilometers per second, and the structure of these light cones is the same everywhere and at every time. This means that the boundary between events that can be causally connected and those that cannot is uniform throughout all of spacetime. An observer at rest and an observer moving at constant velocity, whether 0.3 c or 0.8 c, may assign different space and time coordinates to the same event, but they still completely agree on whether that event lies in the causal past, causal future, or outside the causal scope of another event. The Lorentz transformations allow differences in coordinates, but they are constructed precisely to preserve the light cone structure and the space-time interval. Therefore, no frame change exists that can turn a causal relation into a non-causal one, or vice versa, in Minkowski spacetime. It is in this context that paradoxes related to superluminal speeds become unavoidable. A superluminal world line is not simply motion faster than 299,792 kilometers per second. It is a geometric object that cannot be embedded in Minkowski spacetime without breaking the foundational structure of the model. Introducing such a line means either abandoning the invariance of the spacetime interval or breaking the absolute boundary of the light cone, and in either case, the resulting model is no longer Minkowski spacetime. Therefore, the fact that special relativity does not allow superluminal speed is not an empirical or technological limitation, but a direct consequence of the flat spacetime geometry established in the early 20th century. In Minkowski spacetime, causality does not need to be protected by auxiliary assumptions or supplementary rules. It is inscribed directly into the geometric structure. Although observers may profoundly disagree about simultaneity, lengths, or measured time intervals, they are still forced to agree on what can influence what. Minkowski spacetime therefore reveals a key point. It is possible to abandon the absolute time of classical mechanics while still preserving an absolute causal order. This very combination makes special relativity a tightly logical theory. However, the real universe we observe is not composed solely of such ideal regions. As soon as we leave the flat Minkowski context and bring gravity into play, the question immediately arises, what happens to the causal structure when space-time itself is no longer flat? This is precisely the starting point of general relativity, where gravity is described not as a force in the Newtonian sense, but as the curvature of space-time caused by matter and energy. Within the framework of general relativity, completed by Albert Einstein in 1915, with the publication of the field equations, the geometry of space-time changes fundamentally. The paths of matter and light are no longer straight lines in flat space, but are curved by the presence of mass and energy. However, the key point to clarify from the outset is that this change does not eliminate causality, but places it within a broader and more sophisticated geometric structure. In curved spacetime, we can no longer apply the simple Minkowski geometric concepts introduced by Hermann Minkowski in 1908 globally. There is no single inertial reference frame that can cover all of spacetime, especially in cases of strong gravitational fields. Nevertheless, an important result of general relativity is the equivalence principle, proposed by Einstein as early as 1907, which shows that in every sufficiently small region of spacetime, we can always approximate the geometry as flat. This means that in the sufficiently local neighborhood of every event, spacetime still resembles Minkowski. Light cones are still clearly defined, and the distinction between time-like and space-like directions remains intact. The causal structure therefore continues to exist locally, even when the global geometry becomes complex. In general relativity, the world lines of massive objects and the paths of light are no longer straight, but are geodesics in curved spacetime, determined by the Einstein field equations. No matter how curved they are by gravitational fields, every valid world line must still lie within the local light cones at each point. No segment of a physical world line is permitted to extend beyond the local light cone without violating causality. This shows that the speed of light limit, approximately 299,792 kilometers per second in vacuum, is not eliminated in general relativity, but is applied locally at every point in spacetime. The important difference from Minkowski spacetime lies in the fact that light cones are no longer parallel and uniform throughout all of spacetime. They can tilt, rotate, and deform as we move from one region to another, reflecting the degree of curvature of space-time caused by matter and energy. This very deformation makes the causal structure in curved space-time richer, yet no less rigorous. Concepts such as causal past and causal future remain defined, but they depend on the global geometry of space-time rather than on a single flat structure. In familiar cases, such as space-time around the Earth or the Sun, where the gravitational field is relatively weak, the curvature is small, and the causal structure closely resembles Minkowski. Relativistic effects in these situations, such as gravitational time dilation first measured in the 1960-pound Repka experiment, are merely small but measurable corrections. However, when entering regions of strong gravitational fields, the curvature of space-time becomes significant, and light cones can tilt extremely. This leads to important consequences for the ability of events to influence each other. Light can be bent, world lines can converge or diverge, and regions of space-time can become causally separated in ways that do not appear in flat space-time. Even so, the basic principle remains. No signal or physical influence is permitted to cross local light cones. General relativity does not allow causality to be violated. It only allows causality to be organized according to more complex geometric structures. This becomes especially important when considering extreme solutions of the Einstein equations, where the curvature of space-time is no longer a small correction, but dominates the entire geometric structure. In these solutions, space-time can exhibit causal horizons, boundaries beyond which outside observers can no longer receive influence from events inside. Such horizons do not exist in Minkowski space-time, but are natural consequences of curved space-time. They do not break causality, but restructure it on large scales. A key point is that in general relativity, causality can no longer be read directly from a simple global space-time diagram with universal axes. Instead, to determine whether one event can influence another, we must examine whether a time-like or light-like geodesic connects the two events within the specific geometry of the space-time under consideration. This makes causal analysis more subtle, but by no means ambiguous. On the contrary, it forces us to work directly with the geometric structure of space-time. It is in this context that concepts such as light cones, proper time, and world lines become more important than ever. They provide local tools that allow tracking causality, even when space-time is strongly curved. And it is precisely when these tools are applied to solutions with extreme gravitational fields that we see the causal structure pushed to its limit without being broken. The increasingly strong deformation of light cones in curved space-time leads directly to the most extreme scenario that general relativity permits space-time around and inside a black hole, where the causal structure becomes a direct test of our central question, whether causality can be broken when space-time geometry is pushed to its limit. In space-time, around a black hole, especially when considering the simplest Schwarzschild solution, the first thing that draws attention is the change in the roles of space and time when crossing the event horizon. Outside the black hole, the familiar structure still holds. Time defines the inevitable direction of word lines, while space provides directions of motion within the limits of the light cone. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers, and all outside observers agree that valid word lines can enter or leave regions with radii larger than that value. However, as we approach the event horizon, the light cones begin to tilt systematically. Outward directed light rays become increasingly difficult to escape, until at the horizon itself they become tangent to the horizon surface. This is not a dynamical phenomenon, but a geometric sign that the causal structure is entering a different regime. When crossing this boundary, the rearrangement becomes radical inside the black hole. The direction of decreasing radius, which was once a spatial direction, now becomes a mandatory time direction. This is often succinctly described by saying that space and time swap roles, but that phrasing is easily misleading without geometric explanation. In reality, there is no reversal of causality or backward flow of time. Instead, the light cones have tilted to the point where every time-like word line is forced to point towards smaller radii. Moving deeper into the black hole is no longer a geometric choice like turning left or right in space, but is equivalent to advancing into the future in the causal sense. That is why the impossibility of escaping a black hole has nothing to do with lack of energy or technological limits, but is a geometric necessity. No valid word line exists that would allow an object inside the black hole to increase its radius, because that would require the word line to reverse along proper time. Every observer, regardless of whether they use Schwarzschild, Kruskal, Sekeres, or any other valid coordinate system developed in the 20th century, agrees on this point, because it does not depend on coordinate assignment, but on the structure of space-time itself. This is the crucial point, showing that even in the most extreme environment, general relativity allows, causality is not violated. On the contrary, it is enforced more strictly. Events inside the black hole are still arranged in a clear causal order. Events at larger radii always lie in the causal past of events at smaller radii. No frame change can reverse this order. The event horizon is therefore not a physical wall or a place where local laws collapse. For a freely falling observer, crossing the horizon comes with no special signal, just as analyses from the mid-20th century have shown. However, in terms of global causality, the horizon is a real boundary. An event inside cannot influence any event outside, not because something blocks it, but because no valid word line connects the two regions in the direction of increasing proper time. This is the natural extension of the light cone concept in curved space-time. Even when considering the central singularity, where in the classical description quantities such as curvature become infinite, causality is not overturned. The singularity is merely the point where time-like world lines end, marking the limit of the classical description rather than the collapse of causal order. Therefore, the black hole is not an exception to the principle of causality preservation, but the strongest illustration of it when space-time geometry is pushed to its extreme. Causality does not disappear, but becomes inescapable. From the beginning of the 20th century, when Albert Einstein published special relativity in 1905, the fact that time and space became quantities dependent on the reference frame was never allowed to drift arbitrarily. They were tightly bound by a new quantity, the space-time interval, clearly presented by Hermann Minkowski in 1908. And this quantity has a key property, invariance for every inertial observer. It is from this invariance that the causal structure emerges not as an additional assumption, but as an inevitable consequence of space-time geometry. Concepts such as world lines, proper time, equal interval hyperbolas, and light cones are not disjoint pieces assembled later, but different manifestations of the same foundational geometric structure. In flat Minkowski spacetime, this structure reaches its simplest and most symmetric form. Every event has the same light cone, the same for every observer, and the boundary between what can and cannot causally influence is absolute. No Lorentz transformation, whether written in equations or drawn geometrically, can alter that boundary. When extended to general relativity in 1915, space-time geometry becomes curved. Light cones can tilt and deform, and new global features such as event horizons appear, clearly described in the Schwarzschild solution of 1916. However, even in these cases, the foundational principle remains, At every sufficiently small point, causality is determined by the local light cone structure, and every physical world line must respect the increasing direction of proper time. Black holes, far from breaking this principle, show how strictly it is enforced inside the event horizon. Decreasing radius becomes a mandatory time direction, and every world line ends in its own future, with no exceptions and no possibility of reversing cause and effect. The paradoxes often associated with ideas, such as exceeding the speed of light or reversing time, do not appear randomly. They only arise when we deliberately break this geometric structure. Allowing a world line to extend beyond the light cone means abandoning the invariance of the space-time interval or the relativity principle. And at that point, we are no longer working within the framework of relativity. Within the very framework built and tested for over a century, superluminal speed is not merely something not yet technologically achieved, but something structurally incompatible. The entire chain of reasoning leads to a clear physical conclusion. Relativity does not make everything relative. It allows coordinate time and spatial distance to depend on the observer, but in return, it locks causality tightly into the geometry of space-time. Causality is not protected by ignorance or technical limits, but by the very way the universe is organized at its deepest level. Therefore, in the universe described by special and general relativity, breaking causality is not an unexplored possibility, but an impossibility. If you want to continue with me exploring the deepest structures of modern physics and understanding why the universe operates so rigorously, please subscribe so you don't miss the next episodes. See you again in the next exploration, where we will continue to test the limits of what seems impossible.